All right, let's go ahead and get started here. So thank you all for joining us today on our webinar for designing a secure cloud-enabled peer-to-peer IoT application. I'm Jen, and I work with the OpenDDS team here at Object Computing. We are so happy to have our presenters, Adam Mitz and Justin Wilson, here with us today. Adam is a partner and distinguished engineer here at Object Computing, as well as the product lead for OpenDDS. Justin is also here with us from Object Computing, and he's a principal software engineer and works with the OpenDDS team. As a reminder, please load up your questions into the Q&A section, and we will be doing a live Q&A session at the end, and we'll answer as many questions as we have time for. Adam, I'm going to go ahead and turn it over to you and let you guys go ahead and get started because I know you are eager and we have lots to cover.
All right, thank you very much, Jen, and thanks everyone for joining us. So here's our agenda for this presentation. We're going to look at the application requirements and preliminary architecture. So what is it that we need to build for? And then in step 2, design alternatives. So what existing solutions are out there to help us implement the application, and why might we pick one over another? In point 3, the solution overview, what we actually implemented for a real project in this space. 4, going into the details of OpenDDS features used in the solution. And 5, we'll wrap up with some lessons learned and conclusions. So we need to start with defining what is it that we are trying to build. So imagine that you are in charge with designing a software system for home automation and security. So we'll have a user, and the user is going to need to interact with their software either on a mobile phone, on a tablet, through the web. And what does the software control? Well, it's going to control things around the home. They may be, locks or lights or cameras or motion sensors, or you can imagine other use cases involved in this as well. So what are the requirements of the system, kind of at a high level? From a user point of view, the user wants a good low latency experience, right? We're doing a lot of real-time interaction with the physical world. So it's not where we're just putting data into and getting data out of databases on a server somewhere. It actually has these interactions with the observable world, like turning on a light or unlocking a lock. So when the user presses a button on the touchscreen of their smartphone, we want to see that impact in the real world as soon as possible. Of course, data flows in the other direction as well. So if things change in the real world and there's a sensor, an indicator for that, we want that to show up in this example smartphone as soon as possible. We also have requirements for remote access, right? So we expect our devices to work everywhere. Smartphones, for example, they could be in the home, so they might be on the same network as some of these things, but we also expect that leaving that home network, all of these applications will still work. Of course, security is always important, so we're providing ways that these real-world devices can be connected to the internet, so we have to make sure that it is secure and only authorized users can control these devices. And the system needs to be evolvable, right? So different applications and different versions can be in play at any given time. I think that's true of lots of distributed systems, but it's definitely good to think about from the start. Right? We can't assume that everyone has, for example, the latest version of the app that's available for their smartphone installed, right? Some people may not have gotten the new version yet, so the older version has to keep working. And we'll talk through some of that a little bit later as well. So what about from the operations point of view, right? So our example company that's going to be producing and fielding these devices needs to operate and maintain the system. So we need to think about device administration, things like firmware upgrades and log collection. we need to be aware of cloud costs, right? Because, as we'll see, there's going to be some cloud components, and the way we choose to use the cloud will have a direct impact on our costs. So if we're offering a paid service to subscribers, we want to make sure that that's still profitable and sustainable long term. But even more so, if the end users are only buying equipment once and don't have any recurring subscription costs, then we want to minimize our operational cost, again, to make this a sustainable solution. Also, from the operations point of view, we're interested in having a common technology stack so that we can develop the software needed across the distributed system without adding different technologies for different use cases. And we'll get into what we mean by that in a moment. So let's sketch out a preliminary architecture. And of course, the cloud icon here showing that various components may be cloud resident, but we'll also think about the applications that the user directly interacts with. Just to simplify, we can think of this as running on a smartphone, although it wouldn't have to be. And we'll also think about, on the left here, a gateway. So what we're calling a gateway may be an actual physical device that's deployed in the home as a gateway, or it could be more of a conceptual thing where if we are supporting something like a camera, maybe the gateway components is just part of an embedded CPU inside this camera system. For the sake of discussion here in our presentation, we are going to think about the gateway as a distinct component. There's some advantages to that, right? It can serve multiple of these devices all at the same time. But of course, you wouldn't have to, right? There may be some cost advantages to not having an actual separate device as the gateway. But again, in our kind of conceptual architecture here, the gateway is a thing that can communicate with the cloud, with the application, right? It has an IP address of some kind. And so this is our kind of overall sketch, right? We know we're going to have some kind of APIs for interacting with the device, for interacting with the user, and we'll see how we want to actually use these things in the actual solution. And so the problem to be solved here is essentially this dashed triangle in the middle, right? What kind of technologies do you want to use to have the app communicate with the gateway, either directly along this horizontal dashed line or with the help of components running in the cloud? So let's look at the details of this problem. We know the gateway is a device installed in the home, right? It has some connectivity to the internet. Most likely, we're going to find that this is installed behind network address translation and firewall. That's what we'd expect from a home network. And we see the app as a mobile application, right? Running on a smartphone or tablet. And it may be on the same network as the gateway, right? And so if the user is at home, and that may be quite often, or a large percentage of the time that the user wants to interact with these devices, they may be within the home network, but they can also take this mobile application outside the home, right? And that's connected to Wi-Fi or mobile data. So one of the main problems we're trying to solve for is how should these two components communicate with each other? Should they send messages through the cloud or exchange the messages directly, or do we need to support some combination of these things? And along the way, we can't forget the cloud-hosted application part of this, right? So going back to this diagram, right, if there are components that are cloud resident that also need to communicate with the gateway in the application, we want to support those as well. So let's break down some of these particular issues, and we'll see how existing tools, techniques, and protocols can address them. So first is discovery. So how did these two components, right, primarily we're talking about the gateway and the mobile application, find each other? So in a local network scenario, there's a number of tools available to us, things like MDNS, zero conf for bonjour, universal plug and play. There are these various techniques that have been developed and are common in the industry. But in a cloud-based scenario, right, or when the mobile app is outside the home, a lot of these solutions that would depend on IP multicast are no longer feasible, and we can think of doing things like REST-based services that are accessed at a well-known location. So we're thinking about these kind of things for discovery, right? We need to sort of bootstrap the system and get the two devices to know where each other is. But we also have to think about security. So how do we know if this particular app user is authorized to communicate with this particular gateway? And there's a number of approaches that can work for this, right? Maybe the gateway itself can decide, right? Maybe it's provisioned with some certificates that identify what the authorized users are. Or maybe there's something in the cloud that can tell the gateway if a particular user is authorized, right? So different approaches here, there's various trade-offs, and we'll see more about that later. So once we've taken care of some of these infrastructure needs, like the discovery and security, we can think about the data flow. So two directions of data flow that here we'll call commands and notification. So commands is if the app wants changes on the gateway, right? So for example, it wants to tell the gateway that the smart lock on the front door should be locked, right? So should it be sending HTTPS? Should there be a post for that? Or should we employ a messaging system like an MQTT, COAP, or AMQP? And then going along with that, what about notification? How about the other way around? And this is a little bit trickier, right? Events that occur on the gateway or the devices that the gateway is serving, how are those events relayed back to the application, right? So HTTPS isn't really made to do this directly, but you can simulate it with polling. You could employ WebSockets, and you can even use the same kind of messaging systems that I just discussed a moment ago, right? The MQTTs. And all those are possible. So when looking at all these different protocols, techniques, and existing libraries that can be brought to bear on this problem, we need to think about how we want to evaluate the different options available to us and why we might choose one over another. So the 5 areas we've identified here for evaluation are listed on this slide. So we have generality, right? Does the same protocol work both when we're local, right? We're on the local network and we go outside the local network. Are different qualities of service supported with it? Also, we want to think about infrastructure needs. Are brokers required for this? And if a broker is required, how are we handling the high availability and fault tolerance needs? We have resilience to network issues. So when looking at different techniques and solutions, does it support connecting an authorized app to the gateway even during an internet service outage? Also, we're thinking about efficiency, right? We have that notion of the latency, right? How quickly are commands issued by an app on a mobile device reflect in the real world, and the other way around, right? How quickly are things that are sensed or input into the system from the real world reflected into the application. We can also measure efficiency in terms of like the overall number of bytes that were exchanged, the cloud ingress and egress, which that might correspond to cost depending on which cloud system you're using and how that's set up. Or we could look at efficiency in terms of the impact on the usage of the mobile battery. And we also want to think about abstraction and just kind of the programming model, right? So how does an application developer interact with the distributed systems middleware? Does the application developer need to be concerned with how each byte is encoded? Does the application developer need to be concerned about like an XML or JSON or other string-based encoding? Or can the application just work with the kind of higher level types that we're used to with like object-oriented style programming. So given all these evaluation criteria and all the different alternatives that we have, we might turn to what resources exist that have been developed for looking through these different solutions and how they can all work together and what we might choose. And it just so happens that a group called the Industrial Internet Consortium has gone through a lot of these issues and created a useful document called the Connectivity Framework. And so some of these next diagrams that have this IIC logo in the upper left are from that document. And what it shows is how we can think about the different aspects of the system and how they kind of layer together. What we're seeing is on the left is one participant. We can think of it as our gateway part of the system. On the right is the mobile app part of the system. And the different layers, like you might be used to from like the ISO layered networking model, are concerned with different levels in the system. So down below, things like the physical and link, we're not going to be too concerned with here. Those are supported, both wired and wireless networks exist, and there are different options for them. But we're looking at more of the higher level things today. The network in the middle here is going to be IP. That's why it's a narrower part of the diagram. We don't have a lot of different choices because we are talking about using the internet, and so internet protocol is our network protocol. What we do on top of that, we have many interesting choices. And the IIC connectivity framework breaks these into a few different layers. We've got the transport layer, which is concerned with sending messages across. And on top of that, the framework, which is concerned about a more general sense of data traversing. So maybe multiple messages could make up one piece of data, being it a state change or event or stream that's traversing the network. And then on top of all of that, we have this distributed data interoperability and management layer, which is more about what the application wants to do with the middleware. So we'll focus on these two for a moment, framework and transport, and see what concerns they both address. And so we'll start with the transport, the one shown in green on that. And if we break open the transport and see what's inside of it, here we're thinking of things that are fairly low level, right? We need some kind of messaging protocol, how our message is formatted in the system, and to address some of the basic mechanisms of security, of addressing, does it provide some kind of virtual sense of connected sessions across a connectionless underlying network? All those sorts of things are handled by the transport. But notice that this does not handle some of the higher level concerns, and that's what's in the framework layer. So in the framework layer, we have things like policies over on the right, quality of service and security policies. We also have things along this bottom edge, like the data type system, identity and addressing of the data, a resource model, and paradigms like publish, subscribe, and request and reply, handling discovery. So all of these higher layer concerns are still important. And the reason they're addressed here within framework is that they are still common across many different kinds of IoT applications. And there are things that could be done within the application, but since they are common, it's much better to have them as part of the middleware so they can be written once and reused across many different applications. So bringing all that together, we can look at different industry solutions and kind of where they fit within this notion of the network layer, the transport layer, and the framework layer. And obviously there's a lot out there in the industry. We're not necessarily saying that this is an exhaustive list, but a lot of the sorts of protocols and tools that might be considered are listed here. In particular, it's important to consider both a framework level solution and a transport level solution. so that things that provide only a transport level solution are not addressing some of the common concerns of the framework layer. And as you might be aware, in this discussion today's webinar, we are talking about what's in the red dashed box here. So the selected framework in this application is OpenDDS, configured for the RTPS transport, and that runs on top of UDP-IP. So since we are talking about OpenDDS and how it's used to address these needs of an IoT application, let's talk a little bit more about DDS and OpenDDS so that we all have some common background in terminology and how these systems work. So OpenDDS applications efficiently share data across the network using strongly typed and asynchronous cache updates based on topics and quality of service policies. In this diagram, we see that a number of robot arms are all part of a distributed system. So the different robot arms are doing whatever they need to do, whatever robot arms do, and they are interacting with different topics on the network, and sometimes publishing, like the telemetry or the system status, or sometimes subscribing, like receiving a shutdown command. And the servers over on the right obviously have other software running on them that interacts with the system. So we see the circles with arrows kind of flowing through the system, showing our what we call data samples, right? Individual units of data that are read and written on the different topics. So a few other DDS terms that will be important for our discussion today. In this diagram, we see an example system that has two different topics, tracks and sensors, and various readers and writers that interact with those topics. So when we think about the sender of data on an individual topic, that object is called the data writer in the DDS API. Those are seen on the left. Similarly, the receiver of data is called the data reader. And notice that each data writer or data reader is associated with a specific topic. So we think of those topics as kind of how the writer and the reader coordinate with each other, right? How do they agree on what kind of data they're dealing? The overall data space is called the domain. So we've shown that in the rectangle around the whole thing. And the access to that space within a given application is done through an object called the domain participant. We'll often just call that participant for short. Okay, so we'll come back to this diagram, the preliminary architecture, and then see how OpenDDS can meet these needs. And for that, I'm going to turn things over to Justin. So go ahead.
So in the remainder of this presentation, we're really going to be looking at different aspects of our application and how and where DDS applies to those, and in some cases where it doesn't apply. Again, recall our architecture. We've got our gateway, we've got our app, we've got local interaction that we hope to achieve, we've got relayed interaction, and we have some APIs that are also there to service this gateway and this app. So let's go to the next slide and let's think about the local interaction. So in DDS parlance, we have our participants. We'll have a participant running on the gateway. We'll have a participant running on the application. Since we're using RTPS, we'll use its discovery, which is based on multicast, to allow those two participants to discover each other. In this particular case, the application will be using DDS Security. So as part of that discovery process, they will authenticate each other. Their data readers and data writers will associate, and then they'll start exchanging data. As we've already said, the RTPS stands for real-time publish subscribe, and it's an interoperable wire protocol for DDS that supports DDS security. So any vendor that conforming to those, the DDS spec and the DDS security spec, can provide software that would interoperate in this environment. So this solves our local interaction. Our next interaction that we want to consider is the remote interaction. So in this particular case, our participants are now behind two different firewalls, potentially, so they can't send multicast and they can't discover each other that way. So we think of our cloud relaying component, but in this particular case, we're thinking that it can just relay RTPS messages. So that we send an RTPS message to the cloud, and the cloud then forwards it to the other participant for whom it is ultimately destined. What we want out of this is some horizontal scalability, so that as the number of gateways and the number of applications and users increases in our system, we can keep expanding that relay to accommodate that load. And it also obviously needs to support DDS security to prevent unauthorized use. But other than that, it's completely generic. Okay, so moving on. So the third interaction, and this is kind of between the two, is the idea that two participants can interact from firewall to firewall. So they can do this using a technique called interactive connectivity establishment, ICE. And this is a protocol that is based on a similar protocol called STUN, which allows them to perform connectivity checks. So by performing these connectivity checks, they can essentially form a connection from firewall to firewall and not necessarily use the cloud to relay every single message. And that is a potential savings, whereas since the cloud is no longer sending data out, and I'll talk a little bit more about that later. ICE does require a third party. In this particular case, our RTPS relay will be that third party that allows the gateway and the application to exchange discovery information and bootstrap this protocol. So let's move on to the next slide. So in that particular case, we've really focused on that the triangle of just allowing the app to talk to the gateway. However, there's other APIs, and in particular REST APIs, that we may want to produce for our app and our gateway. First, there's going to be an identity and access management, IAM, system to support the gateway and the application. And so for example, the application needs to authenticate to the cloud so that it can onboard gateways or do other administrative things. And similarly, a gateway may want to access the cloud to perform operational things such as uploading logs or downloading firmware or downloading a new configuration, perhaps to put it into a debugging mode or something like that. And they may even have an API that is integrated with the RTPS relay for the purposes of load balancing. So most of the APIs that I'm talking about here, if not all of them, are well suited for REST API. That's a well-established technology, and there's a lot of ways where you can build a very solid REST API. So find the technology that's right, for you, for your project and your team, and run with it. So in that particular case, I'm not necessarily going to dwell on the REST aspect, because it is more or less a solved problem, and it's more of the device or application's relationship with the cloud as opposed to the application and devices relationship with each other. So let's move on. So to kind of pull all that together, right? We've got device APIs, we've got APIs to support our users that are running in the cloud. We have this RTPS relay that allows them to communicate with each other over the cloud. But the real driver in this solution is this local interaction, because by avoiding the cloud, we're decreasing latency, avoiding network hops, and we're also minimizing our cloud spend, because not every message is going through the cloud, and therefore we don't have to pay in terms of network, and we also don't have to pay in terms of the CPU utilization that might require. We're also achieving our goal of having a common technology stack, by using the same kind of RTPS protocol with DDS for a local interaction and a remote interaction. From a participant's perspective, it's the same. It's merely just forwarded in a different way. So from here, we'll start thinking more about how would we go about building the gateway and the app, and some of the features we may want to employ when building the gateway and the app. So Adam introduced the basic DDS concepts. For our purposes, we can think about two kinds of topics. We can think about status topics, where the device is going to be writing these status topics, and we can think about control topics, where the application wants to control a device. So the gateway is going to write a status topic. The application is going to read the status topic. The application is going to write a control topic, and the gateway is going to read a control topic. So we'd mentioned the idea of quality of service, and DDS has a variety of QoS policies to tune the relationship and the communication between a data writer and a data reader. In this particular case, our status topics are going to be durable and reliable. Durability means that the current state is always available, so that whenever the application is started and connects to the gateway, it can receive the most up-to-date samples, most up-to-date status for all of the devices, as opposed to waiting for some kind of periodic message to go out. Reliability means that it will keep trying to send the sample over and over again until the other side acknowledges receipt of that. For our control topics, we would just want them to be reliable. We don't want necessarily the last setting written to always be communicated to the gateway. If two users, one wants the lock locked and the other one doesn't, and they're connecting and disconnecting, that would be obviously chaotic. So these different QoS policies allow you to customize and control that. And this is the basic structure that you would have for structuring your gateway and your application. Okay, let's move on to the next slide. So we've already mentioned the possibility that you will have gateways and applications of various versions all running together and interoperating. And from a DDS perspective, what we need to accommodate is the possibility that the definition of a topic is going to change over time. So for example, if you were doing this 10 years ago, or maybe even a little bit longer than that, a light control would simply be a simple Boolean that's saying its state, whether it should be on or off. With new LED lights and advances in lighting, we can adjust the level or the intensity of the light, and we can also adjust its hue, the temperature. So by using a DDS spec and technology that's implemented in OpenDDS called extensible types, or XTypes, we can plan for changes in the structure of the topics. So in this particular case, we annotate our topic saying that it's mutable, meaning that we may add or remove members to it in the future. And we provide a way for identifying the members across changes. In this particular case, we take the hash of its name. So in doing this and allowing this type of extensibility, the readers can supply defaults for a missing field. So for example, if it's expecting a level and a temperature, but the light controller doesn't have that, it can supply those. Or if it's not expecting those, it can also ignore those extra fields. So XTypes allows the definition of a topic to change over time while retaining backward and forward compatibility. The other big piece in all of this is DDS security. So like any security system, it provides two basic features: authentication, proving that this participant is who they say they are, and authorization, making a decision as to what they're allowed to do. So for DDS security is based on public key cryptography. So each participant has a private key and a public key, And these are issued by a mutually trusted certificate authority. This allows the gateway and the application independently to authenticate one another because they both trust the certificate authority. Therefore, they can verify the certificate that is bared by the other. Beyond that, once authentication is complete, we then have to move to authorization. So for DDS Security, authorization is broken into two pieces. One is a governance file that sets a global policy that's shared by everybody. And this says what this governs how RTPS works at a network level, and also it defines certain things about topics that everyone needs to agree on for interoperability's sake. That applies, the governance file is global, and then within that, each participant has a permissions file that describes how they can interact with the domain. So this describes what privileges a participant has. These two documents are signed by a mutually trusted certificate authority as well, that allows each side to validate it, called the permission CA. The permission CA can be the identity CA, or they can be different. There's pros and cons to both of those, but that option is available. So let's move on. So let's look at a governance file. So the governance file answers various questions. First of all, is authentication required? If you're interacting with legacy systems, you may need to not require authentication to interact with legacy. However, most things will want to require authentication. The next thing we need to agree on is how are RTPS messages treated? Are they sent in the plane, which would not be very secure? Are they signed, which would at least prevent tampering, but they would be visible, or are they encrypted? And below the RTPS level, we can then start thinking about various topics. So these topics are written in the form of a wildcard, so you can apply rules to a broad range of topics to avoid, repeating rules. But the basic things you're configuring there are: should liveliness and discovery messages use secure endpoints? Does a reader or writer need explicit permission to write and read the topic? And are RTPS submessages and data payloads plain, signed, or encrypted? So you have different choices in terms of at what level you want to apply a protection, either at the entire message level, the submessage level, or the actual payload of the data. And then what kind of security do you want to apply, whether that's plain, whether it's just signed, or if it's encrypted, if you need the privacy of that. So that's the governance. We now move on to the permissions file. So the permissions file says what a specific participant has. So it identifies whom the permissions apply. In this particular case, it agrees with their public certificate. When it says when the permissions are valid, it says which topics and partitions this participant can publish and subscribe. We haven't mentioned partitions yet, but partitions are a way to decompose the global data space in a way that's orthogonal to the topics. So in this particular case, our application would have different partitions for the various homes that each user has. So in that particular case, two people that both have the app are not going to be able to control each other's equipment. Rather, it's going to be isolated. They may both have a light status or a light control writer, but they're only going to talk to readers that are in their own home. And partitions allow a way to have the same topic definitions, but separate them. And then finally, what is the default policy for a particular topic? And in this particular case, we can say deny. Those of you familiar with more of web-based systems, the permissions document serves the same function as a JSON web token, in that it gives a participant the ability to do things for a certain amount of time, which is what a JWT typically also does. Okay, let's move on. So I've mentioned a variety of documents. There's 6 documents in total: 2 CAs, a public and private key, a governance file, and a permissions document. So what we have found by doing this, for real, for a client in practice, is that you really need a system to manage all this, and we call that the DDS security infrastructure. And it's really just a web server that provides the CA certificates, provides the governance files, issues certificates, and then issues permissions files to participants. And this allows you to do things like updating a CA when it expires, updating a governance file if necessary, and yes, we did this on a live system and it worked, issuing new certificates when they expire, and issuing new permissions when they change or expire. And I'll talk a little bit about both of those in the next slide, or the next two slides. So for authentication, DDS can use a CRL, certificate revocation list, or the online certificate status protocol. However, industry seems to be moving away from these in favor of certificates with shorter lifespans to avoid the overhead of long CRLs and the overhead of OCSP. So for DDS security, and with the DDS security infrastructure in place, you could use those. However, neither of them are currently implemented in OpenDDS. Or you could issue certificates with short lifespans, or you could issue permissions with short lifespans. If you choose number 3 exclusively, then a participant could do discovery, but it wouldn't then be able to actually interact reading or writing samples. So those are all ways of controlling the validity and forcing things to be revalidated by getting new permissions and getting new certificates. And the DDS security infrastructure allows you to do that. Let's move on. So somewhere in the system, there's a database that describes the relationship between users and their gateways. And I mentioned this within the partitions before. So Alice owns Whiteacre, Bob owns Blackacre, Eve has Greenacre and Brownacre. So somewhere in your IAM database, your identity and access management database, those relationships exist. The DDS security infrastructure brings those out and makes that available in the permissions document so that each participant gets an appropriate permissions document that allows them to interact with the systems that they want. What's not shown here is a table that's also would be Eve's gateway one of them would be in Greenacre and one of them would be in Brownacre. So Eve could interact with both of them, but they would be only interacting with Eve and not each other. Let's move on. So permissions do change over time. You can imagine that database is not static. So it is a good idea to limit the validity of permissions to prevent a participant from getting too far out of date, and forcing it to check to make sure that it is in the right partition and has the right permissions. And you also need to be concerned that someone with a physical access to the gateway should be able to restrict access to it. So for instance, you move into a house, you should be able to go to the gateway and say, I'm the new owner. I want to break the relationship with the existing owner so that they can't mess with my lights and locks and do other things to my house that they shouldn't be able to do. The DDS security infrastructure could be primary or secondary. And what I mean by that is if you only have DDS security documents, then you could use those to authenticate to the web APIs using a client certificate and probably a JWT after that. But you have a challenge if the certificate expires. And it could be secondary if the system contains a distinct IAM solution. Perhaps a user uses their username and password to authenticate. Using those credentials, they could then interact with the DDS security infrastructure to get all of the DDS security documents. And what's nice about that solution is that the security documents are disposable, so you can always start over from scratch if necessary. Okay, let's move on. So the final piece that I want to talk about is this RtpsRelay component, which allows us to forward RTPS messages. So let's think about a gateway starting a relationship with the gateway decides to connect to an RtpsRelay instance. The first thing it does is it discovers the relay itself. There is another participant called the application participant that runs in the relay, and it participates in this kind of discovery. So it identifies the gateway, it identifies all of its readers and writers and their partitions, and it then takes those partitions and forms essentially a routing table so that we know where the gateways and the apps are that have the same partition, so that when we receive a message from the gateway or the app, we know how it needs to be forwarded. That information is gossiped among the different relay instances. We actually use OpenDDS as a back channel to handle that. And then the final component is this handler, which when it gets an RTPS message, it can use this routing table to forward it to the appropriate next hop. So for example, if it comes from the gateway, it goes to its relay. That relay decides that it needs to go to a different relay. When that relay receives it, it decides that it needs to go to the application itself. So based on this architecture, this is horizontally scalable. At worst case, there's always going to be 3 hops for a message. So we can keep adding relay instances to accommodate a growing number of gateways and a growing number of applications. Okay, let's do the next slide. So since this is horizontally scalable, we need to start thinking about how we can do load balancing. UDP load balancing is not very well developed in the cloud right now. They have simple UDP load balancers, but they aren't really sufficient for RTPS and as it is used in DDS. So the approach that we developed to get around that was to introduce a secondary load balancer, which is depicted as config here. And the point of the config load balancer, let me back up. First of all, it's an HTTP server. It interacts with all the relays so that when a new client wants to connect to a relay, it can pass on the connection information for that particular relay. So each of these secondary load balancers are talking to the relays because the relays publish statistics about their performance and their status. So the config can choose the least loaded relay for that, or whatever policy you come up with, and it can then pass that information on. All of those secondary load balancers are in front of a primary HTTP load balancer. So the whole interaction looks like when the application starts, it hits the load balancer with an HTTP request. It passes that on to one of the config servers. That config server chooses one of the relays and returns that back. Now that the application knows where the relay is, it can go interact with that relay directly. And then the cloud relaying of RTPS packets can occur. Let's move on. So just some observations about relaying traffic in general. Gateways are idle 99% of the time. They're not used that much. The second observation is that some form of polling is unavoidable. That is, gateways are going to check their connectivity to the relay, and if that connectivity check fails, they have to do something else. And the third observation is you pay for messages sent by the relay in most cloud providers. You only pay for egress, you don't pay for ingress typically. So based on these observations, we'd really like to avoid the relay when possible. And we started out at the very beginning with that as a goal in terms of reducing our operational costs. And we can do that with local interactions and ICE. Similarly, the response to a polling request should be small. The RTPS relay uses a stun response, which is 96 bytes. So it's pretty small. It could be smaller, but that stun response is giving us some value. And your overall cost model is to model, how much load does an idle gateway cause, and then how much load does an active user cause, and then scale them by your number of idle gateways and active users. And that applies to CPU, and it also applies to your network egress cost. So that is kind of a framework for how you can think about what your application might cost if you're using the RTPS relay. Okay. So, and kind of looking back at the project and projects that have, allowed us to explore this space, this IoT space with DDS, pick a technology that makes sense. Use DDS where it makes sense. And it makes sense to use it with the interactions between the gateway and the app. But it doesn't make sense to use it if you're just pulling down firmware or pulling down or you're uploading a log or something of that nature. So use HTTP and other good solutions for that. Don't just pick a technology blindly, really understand what it's doing and pick the right one. You can't achieve scalability by accident. You really need a good design. You need to be able to model that design, and you really need to be able to test it to ensure that you are going to hit your scalability objectives. If you're using OpenDDS with security, really you should plan to develop a DDS security infrastructure server and tie that to your IAM system. As a further point, I would highly suggest that you integrate the RtpsRelay load balancer with your IAM system, and that allows you some flexibility in terms of maybe having 2 different relay clusters to support, different service tiers or regional forwarding. It also allows you some traceability in terms of, since the relay is a generic component, it doesn't know about your application. But if you put a load balancer in front, then the load balancer knows something about your application and can provide you with some traceability. The cloud doesn't support multicast. So if you're running the relay, you'll have to prepare for converting multicast to unicast for the relay participant, and we have a utility for doing that, and there are other utilities exist as well. You will see IP fragmentation issues across the internet and in the cloud. You can't locally, you can send some pretty large UDP packets, but as soon as those get put on the internet, they get broken up, and there's a lot of IP routers out there that don't forward the subsequent fragments and don't reassemble them correctly. So IP fragmentation is a real problem, especially when you want to move data that's large. And the final lesson is really that RTPS discovery with security can be slow and intensive and expensive. So if the mobile application needs to make some one-off updates, then it might be better to post those to an HTTP server that can then be forwarded to the gateway later. That prevents the mobile device from doing an expensive discovery just to send one small message. Instead, that work can be dispatched to the cloud. Okay, let's move on. So just to some final conclusions here is that web services are useful for device administration activities, and there's a lot of ways to get a good web service developed. So that's a critical component for an IoT application. The peer-to-peer interactions can reduce latency and reduce cloud costs because we're just avoiding the cloud. And that was kind of the theme of this application. Enabling your peer-to-peer interactions in an IoT application requires some solutions for discovery, security, and evolvability. And the corresponding OpenDDS features we use for those are RTPS discovery, DDS security, and XTypes. A fallback to the cloud is necessary in all systems if you want to provide that, connect from anywhere capability. And we address this with the RtpsRelay. You are left with the idea of, do you want a common technology stack, which we preferred by using OpenDDS to accomplish, local connectivity and remote connectivity, or do you want to use different solutions? Do you want one solution for local and a different solution for cloud? We prefer the common one. If you go with a different one, you need to be prepared that you may have impedance mismatch and other problems trying to integrate these different solutions. And then finally, DDS security infrastructure will be part of the application's IAM. So if you are going to develop an IoT application with DDS and DDS security, you need to plan for augmenting your IAM capability to serve these DDS security documents. So with that, I believe we will open it up for questions. Is that correct, Jen?
Yep, that's correct. So yeah, thanks guys. Appreciate your time today. And I'm looking in the Q&A and I don't see anything loaded up here. So it looks like you guys did such a great job explaining things that nobody had questions along the way. We'll go ahead and give everyone a couple of minutes to load those up there. And as you can see here on the screen, we've got some links to our recently established OpenDDS. Oh, I don't think that one's on here actually, the OpenDDS Foundation. But we do have links to the Industrial Internet Consortium, the OMG DDS Foundation, our OpenDDS website, and object computing website. So if you need any more information, you can get to that there. And then you will see links to some upcoming training events that we have going on. So we will look forward to seeing you there. And the guys will hang around. If you have any questions, please don't hesitate to load them up. And if you need to head out, we thank you again for coming, and we'll look forward to seeing you at our next event. So thanks again. All right, we do have a question here. So in the OpenDDS dev guide, they didn't see the XML config. Do you have a place to point them to?
That's right. Good question. It's not part of what we're discussing here today, but I'm happy to answer that. So we didn't talk about how quality of service policies are communicated from the application into the middleware. A little bit out of scope for what we're doing, but I'm happy to answer the question anyway. The DDS specification says that the quality of service policies are part of the programming API. So they're kind of, think of them as parameters that are passed from the application into the libraries. And so the DDS spec itself does not have a way to do XML-based configuration. However, there's kind of add-on specifications that have happened over time that do provide ways to do that, and OpenDDS has support for that as well. So if you do have questions on using it, I think the OpenDDS GitHub repository is a great place to ask those questions in GitHub there, and we can answer the technical specifics for you there.
If you're interested in the configuration for security, section 14 in the dev guide does have the XML if you're interested in the security XML. There's also examples in the code base as well.
Awesome, thank you. All right, well, it is the top of the hour and we want to be respectful of everyone's time. So we're going to go ahead and say goodbye to everyone, and we will see you next time. Thank you so much.